Hey there, 8th graders. Welcome to This Explainer. I am absolutely thrilled to have you here today. We are jumping right into the principles of geometry, and specifically, we're going to take the Pythagorean theorem and actually put it into practice.
Now look, I totally get it. Word problems can sometimes feel like this massive, confusing jumble of numbers and text. But before we get into the weeds, I want you to listen to this proverb. The plans of the diligent lead surely to abundance. What's really fascinating about that idea is how perfectly it maps onto math, and honestly, onto life in general. Being diligent, that just means taking your time, being careful, and sticking with a process even when it requires a bit of grit. So today, we're going to learn how to translate those messy word problems into super clean, easy-to-read right triangle diagrams. Because when you carefully extract the right numbers from a complex story problem and map them all out, well, that careful planning leads to an abundance of correct answers. It's a fantastic test-taking strategy, sure, but more than that, it's a real-world survival skill you're going to use for years to come.
And when I say real world, I mean it's a total game changer. Architects literally use this math to design walls and make absolutely sure buildings are perfectly square. Pilots? They need to calculate exact diagonal distances to navigate safely. Engineers use it to map out the absolute shortest route between 2 points, and drone operators use it to figure out, hey, does my drone have enough battery to make it back diagonally against the wind? Every single day, these professionals rely on the exact same logic we're about to learn to solve massive, high-stakes problems. And today, we're going to figure out how to think exactly like them.
So here is our game plan for today. Step 1, we turn the word problem into a diagram. Step 2, we label the legs and the hypotenuse. And Step 3, we actually solve for those missing distances using right triangle logic. Okay, let's see this blueprint in action.
All right, let's jump into our first guided practice. A 10-foot ladder leans against a wall. The base of the ladder is 6 feet from the wall. How high does it reach? Now I want you to just picture this scenario for a second. Imagine a perfectly straight vertical wall meeting a flat horizontal ground. And then visualize a ladder leaning right across them. When you draw that out, the ladder, the wall, and the ground actually form the 3 sides of a hidden right triangle. The ladder leaning diagonally, that's our longest side, the hypotenuse. And the wall and the ground, those are our legs. Let's move on to the next step and see how this builds out our equation.
Let's actually walk through the algebra together, step by step. It's kind of like a puzzle. In step 1, we plug our numbers right into the theorem. Our unknown height is h, so we've got h squared plus 6 squared equals 10 squared. And remember, 10 is the ladder, our hypotenuse, so it always gets to sit by itself on one side of the equal sign. Moving to step 2, we just do the math. 6 squared is 36, and 10 squared is 100. So h squared plus 36 equals 100. To get h squared all by itself, we simply subtract 36 from 100, which leaves us with 64. Finally, in step 3, we ask ourselves, okay, what number multiplied by itself equals 64? Well, the square root of 64 is 8. So by being diligent with our formula, we've just figured out that the ladder reaches exactly 8 feet high up that wall.
Awesome job! Let's tackle another one. This time, a park scenario. Imagine a park that is 12 meters long and 5 meters wide. What is the length of the diagonal path right across the park? Think about it. You're walking home and you reach this rectangular park. You could walk all the way down the 12-meter side, turn the corner, and then walk the 5-meter width. Or you could think like an engineer, cut right through the grass and take that diagonal path straight across. Challenge yourself here. How do we find that absolutely shortest route? Well, since it's a diagonal cutting straight across a rectangle, we know we're solving for our old friend, the hypotenuse.
Boom! 13 meters. Let's quickly trace the logic that gets us there. We take our 2 legs, the length and the width of the park. 12 squared is 144, 5 squared is 25, add 144 plus 25, and we get 169. Now that 169 represents the diagonal distance squared. To find the actual walking distance, we just take the square root of 169, and the math lands perfectly on a 13-meter diagonal path. Think about it. If you walk the edges, it would take you 17 meters. By cutting the diagonal, it's only 13 meters. You literally just used geometry to save yourself some walking.
For our final example together, imagine you're out on a hike. Direction 1 tells you to hike 9 miles directly east. Then, direction 2 says to turn and hike 12 miles directly north. I want you to visualize the map you're mentally creating right now. You go right for 9 miles and then straight up for 12 miles. When you turn from perfectly east to perfectly north, bam, you've created a flawless 90-degree right angle. So, the big question is, how far in a straight line are you from your starting point?
So the crucial point here is that we're looking for the hypotenuse again, that straight shot back to the start. Let's run the numbers. 9 miles squared gives us 81. 12 miles squared gives us 144. When we add those two squared legs together, 81 plus 144, we get 225. To find your final distance, simply find the square root of 225. And just like that, we discover you are exactly 15 miles from where you started. You see what we're doing here? We're taking entirely messy, real-world situations and organizing them into clean, solvable math.
All right, now it's your turn to take the wheel. I want you to go ahead and actually pause this explainer right here. Grab some paper and jot down these 5 practice problems we've got for you. A ramp, a kite string, a basic triangle, a city block walking route, and a TV screen. Your homework is to prove your diligence. Read every single problem carefully, draw out those hidden right triangles, label your legs and your hypotenuse, and then use the formula to find the missing distances. I know for a fact you can do this. Just take it one step at a time, exactly like we practiced. Okay, before we wrap things up today, let's zoom out a bit. Let's look at the bigger picture behind the HeroesmartAcademy Godly Learner series. The core idea here is intertwining biblical morality directly with your education. But why? Well, because Romans 8:6-7 promises actual peace of mind to everyone who keeps their mind focused on spiritual things. It's really all about bringing your faith and your intellect together. We truly believe that if you apply the exact same diligence you just used to solve those geometry problems to your moral and spiritual life, it leads to a truly abundant life and gives you real, lasting peace of mind.
I want to leave you with this really striking question to chew on. What is the point of being smart and supposedly educated if you continue to make bad choices that end up hurting yourself or others? An education without morality ultimately just leads to pain. True success in life, it requires both. It takes a sharp mind to nail things like geometry, for sure, but it takes a strong spiritual compass to make good moral choices every single day. So as you go out and crush that homework, remember to grow both your mind and your character. Keep seeking out that peace of mind, stay diligent, and I will see you in the next explainer.